This is pretty much the only set of notes that we're going to have in Unit 4. This unit is typically really hands-on, and unfortunately we're going to miss out on a couple of things virtually, although I do have a lab for you to do at home, and we'll go through that. But I want to talk about Earth's core, and basically this is about minerals and how we go about getting all of the things from a mineral standpoint that we have on Earth. Okay, so we start with the geology. So I like this little quote: civilization exists by geologic consent, subject to change without notice. So there are a few things that we have control over on this planet, but geology, not so much. We really don't have a lot of, control over things like volcano eruptions and earthquakes and things like that. But it's really important that we talk about those things. All right, the first thing we have to understand is that the Earth is a dynamic planet. And what that means is that it's constantly in motion. It's not just a rock sitting out in space going around the sun. We actually are moving and changing, and there's some reasons for that. And one is kind of the unseen, what goes on underneath the surface of the Earth. So we have to understand what it is. Now, when we talked about the atmosphere, we talked about the layers of the atmosphere. The reality is that the Earth is not rock and then air sitting on top of it. It's actually one big system. And what determines that is the density and the density of the different materials or elements that make up Earth. So the heavier elements move to the bottom and the lighter ones get toward the top. And as they get lighter and lighter, they're held on less and less by gravity. So this is just kind of a little representation: the core, the mantle, and the crust. So interestingly enough, how did the Earth form? We are stardust. So our star is Sol, and Sol sits right down here in the middle. That's our little star right there. And as we formed from essentially a supernova, or there's a recycling of different minerals that happens within stars. And so as things blew away, they started to cool down, and then they started to form or coalesce into the planets that we have today. Now, this is an early picture of what the early solar system sort of looked like, just a representation. So you'll see there's lots and lots of comets, there's lots of dust, and there's lots of particles, meteors and so forth, that could, or asteroids that could hit the Earth. So what this means is that the early days of Earth looked quite different. So if we look at it here, what you see is that the bottom left picture is sort of how Earth looked. It was molten. In other words, it was really, really hot, and it was malleable and movable, which made it into the round shape that it is. There were lots and lots of particles, and so Earth got bombarded quite a bit during those early days of formation. The bottom right picture shows you what the Earth started to look like as it started to cool. Now, there's different kinds of theories about how the Earth, or hypotheses about how the Earth became a water planet. One is that we were struck by comets that had ice water on them. Some think that it formed from the very beginning. But the thing we know about Earth is that it is water. Like, from the inside out, the rocks are full of liquid water. So we're blue planet with lots and lots of blueness, water. Now, you'll notice in this little picture that they're showing some ways in which the craters began to fill up. So Earth was sort of, I guess you would say, more like the moon or whatever, where you could see the craters. But as things progressed and as things started to change, it looked less and less like filled with meteors and so forth. We still have evidence of that, but less and less as we've gone by. And there's several reasons for that. One, tectonic plates. So we've moved things around. The rock cycle. So we have a lot of rock moving around because of that. Another is biology. So animals and plants moving across the earth, the formation of soil, and all of those processes plus weathering, right? So wind and rain started to really make a difference in how the earth looked so that it no longer looked pockmarked with meteorites. Okay, so how did the moon come to form? There's several theories here as well, but the leading theory is called Theia, or actually it's called the ejected ring theory is the name of it. So Earth was struck by a very large meteor or planet or whatever called Theia. And it essentially, what it did was it hit and then it bounced out. And as it bounced out, it took material with it. So when the astronauts went to the moon, what they discovered was that there were rock that were very much like what Earth had. So it told us that there were particles from the Earth that had moved onto the moon when it struck. Theia was probably fairly large. The moon's about a quarter of the size of the Earth, and so it was probably more the size of Mars. So that's the leading theory. There's several others, but that's the one that makes the most sense. There's one that says it was, passing by us, and then it got caught in our gravitational field and then started moving around. But there's holes with all of these, and so we just don't know. That's the closest idea that we have. So Earth is composed of layers. So that's what you'll see there on the right-hand side. But the majority of the elements are listed over here on the left-hand side. And you'll see the big 8 down here at the bottom. All right. So oxygen is the number one. Almost 50% of the Earth's elements have oxygen involved in them. And this is oxygen not only with water or the oxygen in the atmosphere, but also water. Remember, it's H2O. Also, rock has a lot of water in it, or oxygen in it. So oxygen is a combiner. It works really well with all these other elements down here and then comprises what the Earth is made of. So you'll notice that oxygen is number one and silicon is next. So most of our rock is called silicate rock. Aluminum and iron, calcium, and so forth make up the rest of it. Now think just a minute about the composition of plants and animals. These still play a huge role in our composition. So not only do we need these elements for all kinds of processes that we have in the earth, but we also need them because they help us to grow things and they're part of living. The core. So the core is a very hard, solid, hot center. There's 2 layers. There's the inner layer, which is that solid, and then there's an outer layer, which is more liquid, or what they call semi-solid. And how do we know this? We know this from seismography. So we'll talk about that here in just a few minutes. But so the inner part is, and it's mostly those heavy elements. So nickel and iron make up most of the core. The next level is called the mantle or the mesosphere. Remember, meso means middle. So the mantle has a couple layers also. It has an upper and it has a lower. It's the thickest of the layers, and it's silicate rock. So once again, got a lot of silicon in it, a lot of oxygen, but it's under high pressure and temperature, so it keeps it like Play-Doh, which is the word ductile, or also malleable is another way to state that. So what we come in contact with when it comes to the mantle is the upper part of it, and that's known as the asthenosphere. But mostly we don't. All right, the outermost layer is called the crust, but it's also referred to as the lithosphere, Litho sphere. So the lithosphere. It's also called the pedosphere because we walk on it. So those are just a couple of names for the crust. Now the crust has varying degrees of depth. So you're seeing a picture of the Grand Canyon, and though the Grand Canyon is deep, it is not really far down because the Grand Canyon sits up in the mountainous region of the U.S. It's the thickest at the mountains, and of course the thinnest in the ocean regions. So most of it's silicate rock. Once again, got a lot of iron and magnesium in it, and that is known as basalt rock. There's 3 different kinds of rocks that we'll look at. So once again, you can see that it varies in depth depending on where you are. It can extend up 200 kilometers at the mountains and very thin at the ocean floor. So if you were here, I'd have you do a little bit of looking at different kind of holes. So, but the color super deep borehole is really cool because what they tried to do was they tried to get to the place where the crust meets the mantle, that asthenosphere. So they started digging a hole, essentially, drilling. And it was enclosed in a tower, and they had to stop when they got 7.5 miles down because the pressure and the heat was so great that they couldn't get any more drilling equipment down there. There's another goal by the Japanese right now to see if they can also do it, but they're going through the ocean. So not as much drilling equipment is necessary. We're a little bit closer there, but we still have quite a ways to go. And so these are sort of the unexplored parts of the earth. The ocean itself is highly unexplored. So anyway, Kola is actually up in the Siberian Peninsula, and they've done a lot of diamond mining up there anyway. So why can't we see what's really going on? The reality is that our drilling equipment just can't stand the pressure. So that's it. Now we can do some surmising through seismography. All right. So when as the hydrosphere, so once again, we are a liquid planet. We're a blue planet. And so there are some things that make up the liquid part of the Earth. So when we say it's a dynamic planet, what we mean is that we are moving, constantly moving. And it's because of this that we have our atmosphere and our magnetosphere, which holds the atmosphere into place. And how do we see this dynamism? We see it through volcanoes and through earthquakes mostly, and different processes that are going on. Most of the time, what you'll see with volcanoes is that the magma is going to come up through cracks in the lithosphere and then fall down back onto the surface of the earth and cool down. So our tectonic plates. So the theory of tectonic plates began in the 1960s, and what it says is that there are giant slabs or plates of Earth's lithosphere that move around, bump into each other. They just drift away from each other, and they sort of are like, imagine the boat sitting on a crowded lake, or in a pier, right, where they're moving across each other. Now for us, this is a very slow process, but the Earth is actually not all that slow. So when you look at the overall time frame, it's moving, you know. And what this does is it creates all the land formations that we had. If it weren't for tectonic plates, if we did not have a dynamic Earth, eventually the surfaces would erode, right, or would weather and wear off until we were essentially covered in water all over the place. So because of tectonic plates, we have mountain ranges, we have continents. All of the features that are there on the Earth are because of tectonic plate movement. The mechanism by which it moves is called continental drift. And so what it does is they say if you look at it, you can tell how things fit together. And then at one point we were one big landmass called Pangea. And here's a picture of what they think Pangea looked like and where all of the land formations that we know of currently, where they all sat next to each other. Some of them had to travel quite a ways to get to their current position. And a lot of this was done through looking at the fossil records and how things were put together. So some places that are now cold places were actually very temperate at one point. So how fast are we moving? Well, we're moving only a few centimeters a year, about the same rate that your fingernails and your hair grow, which to me sounds kind of fast. I don't know. I just think that's kind of fast because I know how often I have to go get my hair cut. But if you look at the large picture, we can't tell we're moving around. All right, so this shows you where the breaks are in the tectonic plates. And you'll notice that it's not a smooth, even picture, right? So there are like jagged edges, and they're sort of messy as they move. And what this does is it builds up pressure. So movement happens not smoothly, but rough, right? One important one to note is, well, there's several, obviously, but there's the one that runs right along here, along the side of North America, or the United States, is the San Andreas Fault. And part of it actually extends out into the ocean. Okay, and we'll look at why that's important. But you'll notice along the coast of Alaska and so forth and so on make up that Pacific plate. South America also has this large Nazca plate that meets the South American plate, and at that border there's lots and lots of activity that happens. So the tectonic plates, the major ones are here. You'll notice that they either correspond to continents or to oceans, and then there's some minor ones as well. Some of those, just because they're minor doesn't mean that we don't know a lot about them. So if you look at the Caribbean plate right here, this is the one where the big Haiti earthquake happened several years ago. All right, so tectonic plates meet in 3 to 4 different kinds of boundaries. The first one is a transform boundary, and when you do the gizmo, you're gonna totally understand this. But a transform boundary slides side to side. And that's what the San Andreas Fault is. It's a transform boundary that's sliding side to side. So eventually what that means is Los Angeles and San Francisco are going to slide, and they're going to be right next to each other. A convergent is where you're going to have a heavier ocean plate sliding up underneath a lighter continental plate. Collision, it means that they're going to collide and they're going to form these mountain ranges. Now, they also call the collisional boundary a convergent boundary. And then a divergent boundary, those are the plates that are moving away from each other, and this is causing mostly seafloor spreading. All right, so here's just basically everything I said. So the transform boundary is the two plates sliding side by side. And you'll notice in this picture right here, this shows you that the pressure is building up. So it's not going to be quick. It's going to take some time. And then it's going to basically pressure, and then it's going to slip. And when it slips, it can slip quite a distance. There's some, I'll try to show you in one of our lectures what happened when the San Andreas Fault had a slippage a couple of years ago and what that did to some pipelines. A transform boundary, once again, you'll see that this is an actual picture here on the right of what the San Andreas Fault looks like from above. And you'll notice that these are sliding. The Pacific plate is going to the north, and the North American plate is slipping down lower. Convergent boundaries, so lots and lots of things happen on convergent boundaries. The ocean is moving underneath, or what's called subducting. That's a good vocabulary word, subduction. Subduction is the action that takes place at these convergent boundaries. And it can form lots and lots of different things: mountain ranges, volcanoes, ocean trenches, the whole 9 yards. So what you'll see is this is essentially these convection currents. So up underneath, in the mantle is moving in convection waves. So if you'll remember, a convection wave moves in a circular pattern like this, right? So it's going up and down, much like our atmosphere is doing. And it's this convection action that causes these plates to start to slip and slide like they do. It will start to catch, so it will catch right there, and then it will have a jarring movement. If water's above it, this is where you're going to have tsunamis forming. So the one in Japan was right off the coast. It was about right here when that slipped. And what it did was it caused a ripple of the water, which was then sent into the coastline. Collisional boundary, the Indian and Eurasian plate is what's going on here. So you don't have necessarily the subduction. You're having sort of a raise that's happening. Lots of earthquakes. And then diversion is where it's going to pull apart and the mantle is going to come up through there. And you're going to have lots of new land formations that happen. And it also sends out a lot of energy. And so there are plants and animals that have adapted to using this as their energy source. A hot spot is an area that's within the middle of a plate. So it's not on the boundary of the plate, it's within the middle of the plate. So this is the Hawaiian Islands right over here. And this hot spot, they believe it stays fixed. So it starts here, and then as things progress along, those islands form as they move over the hot spot. So what that means is that Kauai, that northernmost one, is the oldest of the islands. And then they get younger and younger. And right now, the island known as Hawaii sits on top of that hot spot. And there are 2 active volcanoes on there right now. One erupted last year, and we got to see a lot of really interesting things. There are hot spots around the world. Iceland sits on top of a hot spot. Actually, the plates are coming together there. Cool, very cool. There's some in Africa along the Arabian plate there. Yellowstone sits on a hot plate. There's also one called the Eiffel, which is not in Paris. It's actually German, but the Eiffel is a hot spot as well. So several of those. The concern about Yellowstone is that one of these days, we know it's active, right? It's got lots of hot springs and lots and lots of activity going on there. We know that. It's just a matter of when is that thing going to blow. So there's a caldera there, or the top of the volcano, and it's a valley right now, but they're not sure. If that one blows, we're all in trouble. Just forget it. We're gonna just be covered in snow. Ash first, and then snow. Okay, so here's a holistic picture of how that plate movement happens. So you'll see that the magma is moving in these concentric circles, or the circles, or the convection currents. And then that's going to send the magma up. And what this creates then is our rock cycling. Okay, earthquakes essentially are places where the plates are showing us that they're active. So this is how they're distributed, and this is pretty much the basis for why we know plate tectonics is a thing, right? Is because of the distribution of these different kinds of earthquakes. Believe it or not, some of the strongest earthquakes, now you have the Ring of Fire, and unfortunately in this little diagram it's split, right? So the easternmost side is over here, the westernmost side is over here. Some of the strongest earthquakes ever recorded, believe it or not, have been in Alaska. Now, the reason we don't know that is because nobody's there, right? So usually earthquakes affect us when people are crowded around. Now, unfortunately, we like to live on coastlines. And so that puts us in danger of it simply because, you know, that's where water meets land. And also we like to live by water. We need it for so many things. So some of the ones that you probably do know about are the lots of the ones that happen in the Japanese area. There's several in Indonesia. You can see they're just all over. Now, there are tiny ones in here within the United States and other places. Now, the ones that are in Texas and so forth, and I've seen a couple of minor shakes. Those are not tied into tectonic plate activity. They're actually believed to be caused by fracking or the fracturing of hydraulic fracturing. The difference, though, is that those are very superficial, whereas the ones that happen along these plates are very deep, right? So they're significant in how deep those shakes are going to go. I actually have been in in an earthquake in Chile a couple of years ago. We went down there, and that was weird. Like I was sitting in the bed, and all of a sudden it sounded like a garbage truck was coming down the street. I got up and looked out the window. There was no garbage truck. And then, so we heard the rumbling, and then all of a sudden it starts to do this, like shaking back and forth, which is weird. And people were like, what? We had one today? Oh, I didn't even notice. So the earthquake is that sudden dislodging of the pressure that happens at those plate boundaries. This is San Francisco, and this picture on the left was one that happened in 1989. And that actually was a day baseball saved lives. So the Giants, San Francisco Giants, were playing the what's that other town over there? The one on the other side of the bay. You know which one I'm talking about. Anyway, two teams playing out there on the Bay Area. It'll come to me in a second. And they were playing, and so everyone had left their job so they could go home and watch baseball either at home or a sports bar. So nobody was on the freeway. And it's good because this was a double-decker freeway where the top collapsed and there were very few people that were injured. This happened during rush hour, and if people had been out because of baseball, it would have killed a lot more people than it did. So this, though, is a structure from San Francisco as well. And what San Francisco did, they had a big earthquake in the early 1900s. And they took all the rubble and so forth from the buildings, and they basically built new land in a place where they shouldn't have. And so those structures actually were in worse shape than before because they shouldn't have been there. So seismic waves allow us to look at the center of the earth without having to dig down and see it. So because every earthquake causes vibrations, and those vibrations can be felt all around the world. So at seismic stations, they can actually measure them. And what they know is that if the different kinds of waves reach the seismic station, it is traveled through a different kind of material. So let me first explain about the different kinds. We have P waves and S waves. The P wave is a primary wave. It is the first one to come into the station. So they travel very quickly, and they travel like this way, like straight up and down along the line, okay? They can go through both liquids and solids. So P wave doesn't tell us all that much except that it's gone through a liquid and a solid. So if you have someplace on the other side of the world, let's say your earthquake happened over here, and you felt it over here, we knew that it traveled through both liquids and solids. That's expanding and contracting. All right, the S wave, they come in second or secondary, and they move side to side. So if you've ever been in one, you may not feel that P wave first, like going like this, but that S wave is going to come side to side. The difference, though, is that S waves cannot travel through liquids. The liquids absorb it, and so they can only travel through solids. So back to our little earthquake over here, our station over here, if you don't feel an S wave, it tells us that it is at some point traveled through liquid. So what they could start to do is they could internally map the globe or the earth based on whether they could feel those S waves come into the stations. So they move parallel, another reason why they're called P waves, and S waves are shear, meaning they're perpendicular or side to side. And that basically tells you everything that I just said. So the evidence where it's not traveling through tells us that it's probably liquid. If the S wave comes through, then we know that it was a solid. Even the semi-solids make a difference. Okay, by the way, these notes are on Canvas. And then a tsunami is the one that happens when the earthquake happens over water. So you'll see that Japan, so they have their little, the tsunami happened right here off the coast, and then those ripples started to travel down. And they actually were able to get to the Hawaiian Islands, which are right here. And so they could measure how quickly those were coming in. They actually braced for that to happen as well. Now, the big thing with the Japanese tsunami, first of all, it was devastating. If you've ever seen video of it, absolutely devastating. The other problem was that they had their nuclear power plant sitting right at the ocean coastline. So when that tsunami blew in, they didn't have time to shut down the reactors and the coolers, and so that sent nuclear waste spreading out. And the nuclear waste spread out across the ocean. So eventually, cesium and all those other different chemicals, radioactive chemicals, made their way into the ocean. All right, and so that's kind of it. That's all the notes that I have. And so you'll do a couple of gizmos and we'll be good. All right, read the text.